Welcome back to the deep dive. Today we're tackling a really big challenge with large language models, their memory.
That's right. Specifically, how do we make LLM memory work effectively over long conversations, but without the, massive computational cost?
Okay, you brought in some sources focusing on a system called LightMem. Sounds intriguing.
It really is.
Right.
LightMem takes its inspiration directly from the human brain, specifically the Atkinson-Shiffrin memory model.
Hmm.
So the idea is to see how mimicking that helps build a system that's both powerful and efficient.
Because that's the core problem, isn't it?
Mm.
LLMs are powerful, but they struggle with long contexts. They either hit a hard limit, the context window, or they suffer from that lost in the middle issue.
Yeah, where information just seems to fade even if it's technically still in the window. And when people try to add external memory systems, things get computationally very heavy very fast.
Okay, so before we get into LightMem's solution, what are the main sort of failure points in typical LLM memory approaches that LightMem is trying to fix?
Right. There are three big ones, according to these sources. First is just redundant information, meaning the systems often process the raw conversation, warts and all, think filler words, repetitions, just noise. This eats up tokens and processing power right from the start.
Like taking verbatim notes instead of
Yeah.
summarizing. Okay, what's the second issue?
That's about how the memory is structured or segmented. Often systems use really rigid boundaries. Maybe they summarize every few turns or after a fixed number of tokens.
That causes problems.
It can, yeah.
Mm.
Topics can get tangled up if a boundary falls in the middle of one, or a single memory item might be incomplete because the idea is stretched across a boundary. It's not very semantically aware.
I see. And the third problem, you mentioned this impacts the user experience directly.
Yeah, the tight coupling of memory maintenance. If the system has to constantly update, consolidate, forget information during the conversation.
It slows everything down,
Yeah.
creates lag.
Exactly. Every time you interact, it might need to pause and reorganize. LightMem tackles this by copying that three-stage human memory model.
Okay, let's quickly map that out. Sensory memories is like the super fast filter at the input, right?
Yep. Catches everything briefly, filters out the obvious noise.
Then short-term memory is where the active work happens. Processing, thinking.
Kind of like your mental workspace, yeah.
Mm.
Holding and manipulating information right now.
And long-term memory is the big archive where stuff gets stored more permanently and, crucially, reorganized later, maybe like when we sleep.
That's a great analogy. LightMem basically builds digital versions of those stages. Stage one is that sensory memory filter.
Right, aiming to be selective right from the get-go. How does it actually filter?
It uses a couple of steps. First, there's a pre-compressing submodule. It basically throws out redundant tokens.
How does it know what's redundant?
It uses a compression model, the sources mention LLM Lingua 2 as an example, to sort of estimate how important each token is. Then it keeps tokens based on a dynamic threshold, represented as tau.
Okay, so it trims the fat first. Then what?
Then it moves to topic segmentation. But importantly, not rigid segmentation. It tries to group the compressed information by actual topic.
How does it find those topic boundaries?
It uses a hybrid method. It looks for the intersection of two kinds of signals. One is based on the model's internal attention, like where the model itself seems to shift focus.
Okay.
And the other is based on semantic similarity, checking if the new content is actually about something different.
So wait, why both? Why not just use similarity? Seems intuitive.
Well, the research suggests similarity alone can be a bit fuzzy. Sometimes topics drift slowly. Requiring both signals, the attention shift and the semantic difference, makes the boundary detection much more accurate. The sources said it hit over 80% correctness.
And they tested what happens if you remove that step.
They did, an ablation study. Taking out the topic segmentation, even with compression still on, caused a noticeable drop in accuracy, about 6.3% for GPT and 5.4% for Qwen backbones.
So that grouping by topic is really crucial before you summarize or store it.
It seems so. It helps create meaningful units for the next stage.
Which is stage 2. Topic-aware, short-term memory, the active workspace.
Right. Here, those filtered topic-segmented chunks accumulate in a buffer. Think of it like gathering notes on a single subject.
Okay.
Only when that buffer fills up to a certain point, a preset token threshold, the other time does the system actually call another LLM to summarize that whole topic chunk.
Ah, so it's not summarizing every single turn. It waits for a coherent topic block. That must save a lot of API calls.
That's the idea. The sources highlight this topic-based granularity as being really efficient, minimizing those expensive LLM calls while keeping the summaries accurate. Trying to summarize too early, like turn by turn, can apparently mess up the summary quality.
But there's a tricky part here with that buffer threshold. It's not just bigger is better, is it?
No, it's a trade-off. A larger dollar definitely means fewer summaries, which is great for saving cost in computation, fewer API calls.
Bias.
But its effect on the final accuracy, like in question answering, was found to be non-monotonic.
Non-monotonic, meaning it goes up for a bit, but then might come back down.
Kind of, yeah. Imagine making that buffer too big. You wait so long to summarize that you end up with this huge, potentially complex or rambling chunk of text.
And summarizing that accurately becomes harder.
Right. So accuracy might improve as no one or increases up to a point, but then it could drop off if the chunks become unwieldy. Finding the sweet spot for $2 is key, balancing efficiency and quality.
Okay, so once STM has done its summarizing work on these nice topic segmented chunks, where does that summary go? And this must be where stage 3, the long-term memory, comes in, especially that sleep time idea.
Exactly. And this is where LightMem gets clever about latency. During the actual conversation, when inference is happening, it uses what they call soft updates.
Soft updates?
It means new summarized memories are just inserted directly into the long-term memory store with a timestamp. No complex reorganization happening right then.
So it just adds the note to the pile, essentially, and says, I'll file this properly later.
That's a good way to put it. It avoids those costly sequential updates that bog down other systems in real time.
And the filing properly happens during the sleep time procedure.
Yes, during designated offline periods. That's when the system goes through the LTM, reorganizes things, deduplicates entries, maybe abstracts common themes.
And crucially, how does it do this offline update efficiently?
It does it in parallel. Instead of processing the whole LTM sequentially, it can work on different memory entries or queues simultaneously. This massively cuts down the total time needed for maintenance compared to doing it one step after another.
Can you give that example from the sources comparing this soft update to a more traditional hard update? The Tokyo-Kyoto trip one.
Sure. So imagine you're talking to the LLM about planning a trip to Tokyo. Then you suddenly ask about Kyoto. A system with hard updates might assume the Kyoto question replaces or invalidates the Tokyo context.
And potentially lose the Tokyo info.
Right. LightMem, with its soft update, would just add the time-stamped Kyoto information alongside the Tokyo information. It preserves the whole conversational history, which is vital for complex, multi-topic dialogues.
Okay, this all sounds architecturally smart. Filter, group by topic, summarize efficiently, then store quickly and organize offline. How did it actually perform in tests? Let's talk results from the LongMemEval dataset. Accuracy first.
Performance was strong. LightMem generally outperformed the baseline memory systems in QA accuracy. The sources mention gains of up to 9.65% with GPT and 7.67% with Qwen during that real-time soft update phase. And the accuracy held up well even after the offline consolidation.
That's solid improvement. But the really eye-popping numbers were the efficiency gains, right? The cost savings.
Oh, absolutely. This is where the cognitive inspiration really seems to pay off. Token usage dramatically reduced. Up to 117 times fewer tokens needed in some configurations, particularly noted with the Qwen backbone.
117 times fewer tokens?
Wow.
And API calls. That's often the real budget killer.
Reduced by up to 159 times, especially seen with the GPT backbones.
159x.
Yeah.
That changes the economics entirely. Makes complex, long-running conversations actually feasible. What about overall speed?
Total runtime was also significantly faster, reduced by over 12 times compared to the baseline studied. So it's more accurate, way cheaper, and faster.
It really underscores how mimicking that filtering, grouping, and decoupled updating from human memory can solve these core LLM problems.
It seems to be a very promising direction.
Now let's loop back to something you touched on earlier, that relationship between the initial compression and the STM buffer size. You said it wasn't straightforward. What's the final thought for our listeners there?
Right. This is a subtle but important point for anyone tuning these systems. The research found that the best compression ratio depends on the size of your short-term memory buffer, and maybe counterintuitively.
Go on.
For systems set up with a larger STM buffer capacity, they actually got better accuracy results by using a lower compression rate on the input.
Hang on. If my workspace is bigger, I should compress the incoming stuff less, not more.
That's what the data suggested. It implies that if your STM stage is robust enough to handle a larger, less compressed chunk of information, feeding it that richer, more detailed input might ultimately lead to better summaries and better final QA accuracy.
So you can't just tune the filter and the buffer in isolation. They have to be optimized together.
It seems so. Maximizing performance likely requires that kind of sophisticated co-tuning between the different stages, mirroring perhaps how different parts of our own memory system work together. It adds another layer to think about when designing these advanced memory systems.
A fascinating insight. Thanks for breaking down LightMem for us.
My pleasure.